Were there any questions before I start on homework? Usually I get a couple. Did you get one?
Did you work problem 6.8?
Yeah, give me the specs.
I'll show it to you.
Suppose at H. All right, just tell me what the H field is. This is problem 6.8. H is equal to
100 cosine 2 pi x
2 pi x
Yeah.
times 2 pi times.
Okay.
Times what?
10 to the 7th t minus beta x plus pi over 4 in the x equation.
Okay. And what do they want?
E.
All right, from this one, to get it, this is a great problem. What we're doing here is talking about the nomenclature, really the way we describe an electric or magnetic field in both time and spatial coordinates. We've got 2, 4, 6, 8, 10. Okay, we've got the whole class. So to do this, first I'm going to take H and turn it into a phasor, all right? To do it in a phasor, it's not going to be a function of time. It's simply going to be magnitude, 100. Then it's going to be, we suppress this term, it's going to be e to the minus j beta x, right? And it's going to be plus pi over 4. Since that's a phase angle, it's going to be e to the j pi over 4 here. Now I could lump that in there with the beta term as well. I could have minus j times parentheses beta x minus pi over 4. I could do that as well. Matter of fact, I might as well do that. So it'd be beta x minus pi over 4. And it's in the AZ direction. Now, when we look at these two, this is again time domain, that's phasor. So this would be h bar, or h tilde. And it's a vector. Now to get E field, we can do it in the phasor domain. E, remember, was equal to what? It's minus eta, right? Then it's going to be times the direction of propagation crossed into the H field. You remember me showing you that last time, class? This is in the phasor domain you do this. Now if you look at this, did they give you anything about beta at all, as far as a numerical value?
No, sir.
Okay. Well, did they say it's in free space? Did they say any description?
Down in the solution it says since free space is stated.
Okay, if it is in free space, then here's what we can do. We're going to go, in free space, I know that this coefficient right here, and no, forget free space, this coefficient is omega. And that means omega is 2 pi times 10 to the 7th. And that means F is simply omega over 2 pi, or 10 to the 7th hertz. Or it's 10 megahertz. I'm just putting down some things to be known, that maybe we may need these things. Now I look at this, and I'm going to get the direction of propagation. This is going to be it's a unit vector in the direction of propagation. The way you get this is really taking a look at the spatial variable, which is x in this case, and see if it's beta times x. It's going to be the spatial variation in terms of phase. If that's a negative sign, it's moving in the positive x direction. If it's a positive sign, it's moving in the negative x direction. In this case, and we only have an x, we don't have a y in there. So it's moving in the plus ax direction. Everybody follow me on that? Now once we do that, and if it is free space, we also know that the characteristic impedance, intrinsic impedance is just going to be 120 pi ohms as well, don't we, class? If it is free space, right? Everybody on this? You know how to get eta in general. Eta is what? It's equal to the square root of j omega mu over sigma plus j omega epsilon. That's the general form if it's free space. Sigma is 0, the j omegas cancel, you have square root of mu over epsilon, the square root of mu naught over epsilon naught is 377 or 120 pi. So now we do this. And this is going to be 120 pi ohms times this, which is AX, is the direction, crossed into the H field. And I'm using the phasor form of the H field. 100, by the way, is that 100 milli? Is this 100 milliamp?
Yes, sir, it is.
Okay, so there should be, if that's 100 milliamp, it's like 0.1 amp. So I just put down 0.1 here. And then it's e to the minus j quantity beta x minus pi over 4 in the AZ direction. Please watch this. These problems were meant to just get you familiar with the notation and manipulating it. Is everybody with me with what I'm doing so far? Nothing here it's anyway tricky. You just have to be aware of what things mean. Now, when you do this cross product, you'll notice you can take out the constants, the 120 pi and this e to the minus j beta x minus pi over 4, you can take out in front. So, this becomes 120 pi e to the minus j quantity beta x minus pi over 4. And then it's times 0.1, so really instead of 120 pi, just make it 12 pi. You agree with me there? Once I have that, I do the cross product. What is AX cross AZ? Think about it now.
-1.
That's right, X, it's X, Y, Z, and if you go from X to Z, you're going the wrong direction, it's negative, so it's minus AY direction. And that would be the E field. Agreed? What, they ask for phase velocity, what else they ask for?
That's all they asked for.
If it's free space, phase velocity is speed of light. Anything else in that problem? Did you have any other questions about the other problems? I gave you one problem, it's a little tricky.
So can you just turn that back to instantaneous form?
Yeah,
That's
and
what
what do we do to do instantaneous in a nutshell? If we want the instantaneous, it would be what? Function of x and t. What do? We take that magnitude, right? 12 pi, right? Then what are we going to do? It's cosine of omega t minus beta x, right? Plus pi over 4. And it would be in the AY direction, and this would be minus. I'm going to tell you a little trick here. When you see a minus out here, what you can do is go inside here and add or subtract 180 degrees. Because remember, if you add 180 degrees to a cosine argument inside, you really just turn it into the negative of itself. That's the important thing to know. So if you wanted to, you could do this. You could get rid of that minus sign, and you could add pi in here. And then you would have 5/4 pi if you wanted to go ahead. I don't know what the answers are, but you could go ahead and put 5/4 pi here, and that would be perfectly acceptable as well. You could leave it with a negative sign if you want. Now, one other thing about this, just by inspection, you don't see an e to the minus alpha z. You don't see any decay, right? That means it's lossless, right? And in free space, it has to be lossless. All right. Any other questions about the homework? They're meant to just get you familiar, not really challenge you deeply, but there was one tricky one. It was the one that had both x and y in the argument with cosines. Do y'all remember that one, class? How many did the homework? Just level with me. You? Do you remember that problem? Did you have any questions about it? No? All right, well, that's the one where you have to get, can you tell me which problem that was? I wanted to do this one. It had a cosine argument and then had both x and y inside the argument. Do you remember it?
6.7.
Tell me the problem. Go ahead.
EXYT equals
Ex what?
XYT in the operator.
Oh, e of x comma y comma t.
Yeah.
Go ahead.
5 cosine pi times 10 to the 6 t.
Put pi times 10 to the 6.
Yeah.
Go ahead.
Minus 3x plus 2y.
And what direction?
AC.
And what do they want? H field?
Find the direction of propagation.
Okay. Now,
And the H field.
we can get H in a second. Now, I want to first turn this into a phasor. But I'm going to tell you one thing. You can see right here that you have a mixed bag, don't you? You have a minus operating on the x, or multiplying the x, a minus 3, and you have a positive multiplying on the y. What does that almost imply to you? In the x direction, it's going in the positive direction. In the y direction, it's going in the negative direction. Correct, class? Do y'all see this? And you're right. So first we'll turn it into a phasor. If we want a phasor, this is going to be 5, and it's going to be e to the minus j quantity 3x, right, minus 2y, and a z. That's amps per meter, oh, I'm sorry, volts per meter, Z field. Now, does it say, is there anything else in that problem? Does it say anything else? Okay. All right, for this one, I'll show you something. When I look at this, right, you think about this, if we have, this is really, the combination of these two is really V beta times some Z prime. It's the direction of propagation, or, direction of propagation. I'm using A prime, not Z prime. What this amounts to, this combination is going to be minus A propagation prime. Now, if you look at this, this is the x-axis, this is y. I have 3x and 2y here. You'll see what I'm doing. I'm say this. I'll do it this way. I think this will make a little more sense to you. You know that if you have in a system, if you have x and y, and you have any coordinate, then you can talk about something that's a distance rho at an angle theta. Does that make sense to everybody? Now, when you think about this, you could say that rho is really the square root of x squared plus y squared, and the angle theta is the inverse tan of y over x, right? Does that make sense to everybody? All right, now, if you do this, try to do this in a way it's not gonna, hopefully confuse you. When I look at these two terms and I go ahead and get the effective rho, which is beta times, I'll call it the actual direction z prime, it's really the direction of propagation. That it would have a unit, it would be, the wave is actually propagating in this direction. It's going so many x, so many y, but it's going in that direction. So this would be equal to the square root of actually 3x squared plus 2y squared. And then I have square root of 9x squared plus 4y squared. And I can say that x is equal to the cosine of the angle times rho, and y is equal to rho times the sine of the angle. sorry, I'm not trying to confuse you with this, but I'm trying to do something that's in a chapter, later on in the chapter, and I'm trying to do it without making use of that, but be really frank about this, since it's going down to over 3, we'll just do it this way. Then I can see that the actual distance here for the effective beta on this one is going to be equal to the square root of 2 squared plus 3 squared. And that's the square root of what? 9 and 4, or square root of 13. And the actual direction that it's going in would be at a theta value here, that would be minus tan minus 1 of 2 over 3. Can you tell me that angle, by the way? You have a solution for this, right? No, I mean, I posted one on OneNote, didn't I? For this one? This is a good problem. I'm trying to do this, I was trying to do it a different way, but here's how you effectively get it. You're gonna square the betas in front of x and y, the terms, the coefficients, and take the square root to get the effective beta. What is that?
33.69.
Square root of 2 squared plus, oh, that's the angle.
Angle.
33.1 minus 33.1?
0.7.
0.7 degrees. And what is beta?
Beta.
It was a 3, 4, 5 triangle, would be easy. It's 2.
Square root of 13.
What is it? Yeah.
3.6.
3.6. Is that what the answer is? Do you have the answer for this? I'm sure I posted it, didn't I?
Yeah, I didn't look at it till this morning, so.
Do you have the answer or not?
No, not really.
You got, are you at OneNote, on OneNote?
Yeah, I'm looking at it.
What's the answer?
And the answer, it says, 0.83 in the x direction minus 0.55 in the y direction.
Yeah, but he's taking the component in each direction. Did he didn't give you a magnitude for beta?
No.
I'm gonna see.
On the book.
Oh, he wants the unit, that's a unit vector in the direction of propagation. He doesn't give you a beta general? No?
On the back of the book just says the H field in
Oh,
AP.
alright. Does, alright, let me show you. He, for this, when he says to get, he wants a unit vector in the direction of propagation, when we look at this, if we go 3 positive x, 2 down here, but we want this to be normalized, this has a magnitude here of 3.6, right? Follow me? So now I can say this unit vector in this direction, a unit vector in this direction will be actually 3 divided by the magnitude of this, 3.6, and that's in the positive, because it's going in the positive x direction, ax, and then it's going to be minus 2 over 3.6 in the ay direction. Can you tell me what 3 over 3.6 is?
0.83, yeah.
Ax and minus 2 over 3.6?
0.55.
Does he have that?
Yes.
Yeah.
All right, and he's just saying if this is, he's got to normalize this, if this total length is proportional to 1, then the projection of this length onto this axis would be the actual, that's really, when it comes to, here's the actual way it's going, right? So that has a unit, if this is a unit vector, the projection on the x-axis would be the cosine of that angle, right? Times, which is that cosine 33, times, or divided by this, and the projection here would be the sine of that angle times that. I'm not saying this very well, but really the only thing these things are doing is taking the projection. If that's proportional to 1, then this is proportional to what? If that's proportional to 1, then this is proportional to what? When scaling. That's simple. Okay. Y'all see this? I'm not trying to make a big move. I spent a lot of time with this. There's another way to do this, but it's later on in the chapter, and I don't want to do that quite yet. Were there any other questions about the homework? I try to do at least 1 or 2 homeworks every class period, because working problems, usually students that have difficulty with a problem, there's several, working it before the whole class is very useful. All right, today, we go through what I have in mind for us. It should be pretty interesting, I hope. think about with
For,
posting this? Class, what I'm gonna do is distribute a link. You're recording it, right?
Yes, sir.
Can you send me the link?
Okay.
So I can distribute it so everybody can see this?
Okay.
You didn't send it to me already, did you?
I can go back and do it. I posted it on the Facebook page.
Oh, wait a second, but does everybody have access to it?
Did everybody get the Facebook page invite?
I got it.
Did anybody not get it? I don't think I got it.
You joined the group, so.
All right. Oh, then in that case, I'm fine. I have another class. I'm not sure. I'll take them. All right, everybody. I want to take care of that part now. Today, let's see. Last time, did we get completely done with low loss dielectrics? Or not? Did we have complex permittivity? I have a note, this is where I stopped. All right, you had conductivity, right? We talked about conductivity?
Yeah.
All right, work with me on this one, guys. I'm gonna try to follow the book, and it's important that you see this point. This is a tricky one, but this is a concept that's used all the time. Now, in a lot of times, I was getting at this last time, I said that if charges are bound, but they move and vibrate and dissipate energy in the lattice, that's a polarization charge, and it's related to the dielectric. If, like, an electron can flow right through the lattice and dissipate energy, that's real current flowing. Does that make sense to everybody? So, when we talk about dielectric losses, what we do is talk about E sub C, or epsilon sub C. This is a complex permittivity. Complex permittivity. An E complex, this is used to describe losses that are related to polarization. So these charges can't move through. There'll be the complex permittivity will have only a real value at DC, not imaginary. But it's given as epsilon prime minus J epsilon double prime. That's how it's denoted. Now this double prime has to do with the loss, and it's just a way of us really attaching a figure of merit to the amount of loss. So if you look at the equations, Maxwell's equations, curl of H normally was equal to sigma E plus, and then it was J omega epsilon times E, and here what I'm doing is replacing J with sigma E, the way we did it before, and epsilon with J omega, the partial derivative D with respect to T, where I replace D with epsilon E, and I replace the derivative with J omega. Furthermore, I can say this is E, right, times sigma plus J omega epsilon, right? And then I can put in my epsilon complex. So now I have E times sigma plus J omega, and now I'll make that complex. And then it's going to be epsilon prime minus J epsilon double prime here. And then we end up with E. And we have, now notice what happens here. Sigma stays the same. But when I have J omega epsilon prime, that comes over here. But what happens when I have J times J? What is that? -1, isn't it, class? Well, I've already got a minus sign, so it becomes plus. So then I get this, plus omega epsilon double prime here. Now, I broke it out this way for a reason. Remember what I called this curl of H? I gave it a particular name. Anyone? The Maxwell current density, because it has both real and imaginary terms. And note this is the loss. These are associated with loss, and this is simply displacement current. All right. Now that's generally the way you describe a lossy dielectric with a possibility of a real conductor in there. This is almost never used in this form, but now I'm going to say something. Usually, when you have a lossy dielectric, We assume sigma is 0. That's almost always the case. Just remember that. And so now when we take a look at curl of H, it's equal to sigma, it's just simply this, omega epsilon double prime, and then it's going to be plus J omega epsilon prime operating on E. Y'all follow me? I'll break them out a little further. So I'm going to have what I'm going to call the Maxwell current density, which is going to be omega epsilon double prime times E plus J omega epsilon prime times E. And this is going to be a loss current density. And this is really displacement. Now, this is important what I'm about to show you. This is just getting familiar with things. So if I have dielectric material between capacitor plates, I'd like to know something, a way to quantify how good it is. We would like this loss current to be 0, wouldn't we? We don't want any power dissipated in the dielectric. We'd like to get everything we put into a capacitor out of it. But that's not going to happen. So what we do is talk about something called the loss tangent. And this is the horizontal axis, we put what I call the loss current density, or we plot omega epsilon double prime E. And on the vertical axis, we plot simply omega epsilon prime E. That's the displacement current. So this is here, and this is plotted here. And you'll see something like this. And you're going to see that there's an angle here. And if you look at that angle, or really I should say, the tangent of that angle is opposite, or if you think about this, it's the opposite, or it's omega epsilon double prime times E over this, which is omega epsilon prime times E. Or really what I can say is the loss, or this by the way is called the loss tangent. And typical values are like 10 to the minus 3 to 10 to the minus 5. And of course this angle is simply going to be the inverse tangent of omega epsilon double prime, or really forget that, just epsilon double prime over epsilon prime. And this is the loss tangent right here. This is the definition of loss tangent, and if you take the inverse of that, you get I'm sorry. No, that's right. If I take the inverse of this, I get the actual angle. Follow me? Now you'd like the loss tangent, or this angle to be 0. You'd like no current here. You'd like it to be straight up, but it isn't. Do you understand, class? And this is a way to simply pictorially discuss this. So in the book, they're going to have, in the back of the book, you're going to see loss tangent for materials. But it's a strong function of frequency. And the higher the frequency, generally speaking, the greater the loss tangent. It's like hands of a clock. At DC, there'll be absolutely none, if it's just polarization losses. Then as you increase frequency, all of a sudden, this hand starts moving out, 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 out. And then it gets to a point where really the losses become overwhelming, and it isn't even behaving like a dielectric anymore. Now, after that, we're going to talk about conductors. This is all dielectric stuff. So now, when we talk about conductors, and we talk about propagation in conductors and the behavior, how does a wave, or how does electromagnetic wave phenomena behave when you have a conducting medium? First, we have to define a conductor. So if you think about what a conductor is, go back to Maxwell current density. That's equal to J Maxwell. That's equal to really sigma E plus J omega epsilon times E, right? This is conduction current density, and this is displacement current density. You've heard those terms the last time you took EMA, right? So if you have one, you're going to say you've got a good conductor, what you're really saying is that the conduction current density is much, much greater than the displacement current density. That's what you're saying. Now, there's some things that are obvious, like in a metal, what do you think it is? In iron, steel, copper, for most frequencies, just pick it is. It's what? Conduction current density. When you put an electric field that's time varying, a lot of current moves, doesn't it? Doesn't that intuitively make sense to you? That's the reason they call it a conductor. A good conductor has conduction current. If you had something like quartz or mica, that's probably a good dielectric. The verb opposite is true. So when we talk about a good conductor, things like silver, gold, copper, really a lot of carbon fiber things. Not all, but some. Aluminum, steel, and we could probably list a bunch of other things. You could go to brass and all the other things and even talk about alloys, but metals in general are good conductors. And some, if you talk about like graphite, there's one, graphite has long bond one way, short bond the other way. In one direction, that's short bond, it's a very good conductor, in the other way, it's not so good. But graphite's a conductor. There's a lot of different things that are pretty good conductors at almost all frequencies we use. Gold is probably the best. Gold and silver and copper are the most common. So how do you really determine if something's a conductor or not if you were just given something that's, I don't know, piece of material, and I say, do this assessment? Well, the way you always take a look at it, because if you look at these two, really what we have here is sigma plus J omega epsilon working on E, right? So, and everything, the good conductor depends on the frequency, remember that. So if sigma is much greater than omega epsilon, then it's a good conductor. That should make sense to you. Now, from there, I'm going to show you stuff. Now, you're going to be very responsible for this on Friday, remember. These are things I'm showing you. The homework will reinforce what I'm showing you, so on Friday you'll do all right on the quiz. So if it's a good conductor, when you look at things like the propagation constant, do you remember what the propagation constant is, people? Just this is for intrinsic media, for a medium. Anybody remember? We developed it. Anyone at all? When we did it, what did we say? It was J omega mu times sigma plus J omega epsilon, didn't we? And that was equal to alpha plus J beta. This is very important. Now that's what? That's the propagation constant, right? But there's also the intrinsic impedance of the media, and that's the square root of J omega mu over sigma plus J omega epsilon. Right? Now please watch this. This is important. You're going to get tested on this in quizzes and everything. So keep watching this. Now if it is a good conductor, that means sigma is much, much greater than omega epsilon, right? So what I'm going to do is make it a really good conductor. This is an approximation. I'm going to get rid of omega epsilon because it's much, much, much smaller than sigma for a good conductor. So if I get rid of that, now I have this, don't I, class? And this would be for good conductors. This would be the equations. Now take a look at the top one first. I have the square root of J omega mu sigma, right? I want you to note one thing about the square root of j, because it's important to note this. When I have j, really, that's what? 1 at an angle of 90 degrees, right? Or it could be expressed as e to the j pi over 2. Does everybody understand that? It's taking a unit vector and it's cranking it up to, at 90 degrees. It's right on the imaginary axis. Do you agree with me? Now, if I take the square root of j, that's the square root of e to the j pi over 2. Or it's simply e to the j pi over 2 to the 1/2 power, correct? And that means it's simply e to the j pi over 4. Do you all agree with me? With me? All right, what is e to the j pi over 4? Well, that's what? The cosine of pi over 4 plus j times the sine of pi over 4, isn't it? All right, what's pi over 4 in degrees?
45.
What's the sine or cosine of 45? 1 over the square root of 2, right? Get familiar with that. So this is really 1 over the square root of 2 times 1 plus j, isn't it? Okay, y'all with me on this? All right, so I come over here and now I can say really, because that square root of j is just 1 plus j divided by the square root of 2, I can say this is going to be 1 plus j, and then I can take the square root of 2 inside here. So I can say it's square root of omega. Now omega is 2 pi f times mu times sigma, but it's divided by the square root of 2. You all agree with me there? I replaced omega with 2 pi f. I think everybody can appreciate that. And I took the square root of 2 inside, correct? What's this? That's 1 plus j times the square root of pi f mu sigma. Isn't it, class? And that's equal to alpha plus j beta, which means that alpha is beta is equal to the square root of pi f mu sigma. And this is important in a very good conductor, a good conductor, where sigma is much greater than omega epsilon. Alpha is equal to beta is equal to square root of pi f mu sigma. This is very important. Now what about this? What's this one going to look like? I have a square root of j there, don't I? Inside there? So if I have square root of j, now I can go ahead and say it's 1 plus j divided by the square root of 2, but I'll take the square root of 2 and put it inside the root sign. So it's divided by, then it's going to be 2 pi f, I'm replacing omega with 2 pi f, times mu divided by 2. Does everybody see what I'm doing here? And sigma. With me? Now what do you see happening? That means it's 1 plus j, right? And now I have the square root of pi f mu over sigma is equal to the intrinsic impedance. I'm going to say something else. Good luck if you want to try to kill that thing. I've tried before. Doesn't work. Anyway, when I have this, now that means the real and imaginary part of the intrinsic impedance are the same. Also means the angle of 45 degrees occurs there, right? Another way to write this is simply, when I have the square root of j, I know it's going to be at 45 degrees, so I can say it's the square root of omega mu over sigma, and I can just put right here e to the j pi over 4 outside, and I can leave it like that. You follow me? And that is at an angle of 45 degrees. Follow me? So this is going to be the polar form. This is the rectangular form of the intrinsic impedance. And keep this one in mind. We use this a lot. All right, now I've got the intrinsic impedance. I've got the actual conductivity. So a couple other things that are very interesting that you won't believe. Well, you may believe it. Well, let me do it right here. Pay attention to this point. This is where it gets interesting. What what is phase velocity fundamentally? Do you remember? The fundamental definition, we developed that. Remember we took the argument of a cosine, took the argument of omega t minus beta z, set it equal to a constant, then took the derivative, both sides with respect to time to get the phase velocity? Anybody remember what it was? You're gonna need this, Rodney. It's closed book, closed notes. It's closed everything. No electronics, no calculators. I mean, well, I may allow calculators in some of the quizzes, some of them I don't. There's probably no calculators on this one, but I'll let you know in time. Anybody? Phase velocity, the most fundamental one.
Omega over beta.
Exactly. Omega over beta. I'm trying to get you to interact with me so you remember better. That's my goal. It's not to play a game with you. The more you verbally express things, the better your retention is. Trust me on this. All right, now, what's the phase velocity for metals or good conductors? It's omega, but what's beta? Look over there. Can you read it? Somebody.
Square root of pi times F times mu times sigma.
Right. Now, watch. I want to show you how slow a wave propagates into the metal. Not on the surface of the metal, but into the metal. Now, do y'all see here omega can be replaced by 2 pi f? Y'all give me that? With me? Sure. So now that's 2 pi f. Now, look what happens. When I do this, I have pi f, I have pi f. I mean pi f square root pi f. So that means I'm going to have 2 times square root up here of pi times f divided by what? Mu times sigma. Y'all agree? Let me take a typical example. And when I say propagation in a good conductor, if I had a bar of metal here and the wave was coming, the electric field is oriented this way and it was coming in this direction, when it hits, most of it's scattered back, but some of it penetrates in here. The stuff that penetrates in here will propagate into the metal at this speed. It's nothing to do with the surface velocity. So if we take a look at a typical problem, let's look at something like we're going to talk about copper. We want to see what happens at a frequency of 100 megahertz. If you have a calculator, I'd like a little help with this one. So if I want the phase velocity at that, copper is going to have a permeability of about, a relative permeability of about 1. So it's 2 times square root of pi times 10 to the 8th, that's 100 megahertz, divided by mu, which is going to be 4 pi times 10 to the minus 7, and it's times sigma, which is sigma for copper. Does anybody remember from EMAG 1? 5.7 times 10 to the 5.7?
5.8.
All right, this is the funny thing. It's temperature dependent, 5.8 times 10 to the 7, and that's 1 over ohm meters. Now, what is that going to render in terms of a value of velocity, phase velocity? Just take a look at that. 10 to the minus 7, 10 to the 7 cancels, right? I got the pi's canceling. So I really have 1 over 4 times 5.8 dividing it to 10 to the 8th. What do you get for this? Just give me that answer, someone.
4152.3.
4152 meters per second. Forget the 0.2. What's the velocity of the speed of light?
3 goes to the
10 to the 8th meters per second, right? Now take a look at the ratio. What's the phase velocity in metal, this metal, divided by C, the ratio of that, or how much less it is than C? Just divide that by 3 times 10 to the 8th. That's still fast, but
very small. 1.2, 10 to the minus 5 scale.
about 10 to the minus 5. All right, it's 5 orders of magnitude less than the velocity in free space. I can actually show you, for something reasonable, I can walk faster than the wave can propagate into the metal. Because of the way these phenomena work, when a wave is propagating into metal, you got to understand there's a lot of complexity in what I'm trying to describe simply. What you really have is photons. Photons are the smallest little particle of electromagnetic energy. And when they're in a metal and there's electrons and stuff, they're not going in this direction. They're bouncing like, I mean, there's no, you might say, the directionality overall is going that way, but because they are basically in an area where there's such an extraordinary amount of conduction, it's basically going like this. Most of the time, the photons are banging this way, not that way. Now, you're going to have to just take it for granted. It's much more complex than I'm worth to get worried about right now, because when we look at electromagnetic phenomena, we always look at the ensemble or the overall effect of photons, and we call it an E field. We don't take a look at individual photons. It would make no sense to describe the phenomena we're carried about like that. But anyway, that shows you the dire difference when you're talking about velocity and metal. Never you see. If you do, you're just crazy, because you're going to be so far out of whack. The other thing I'm going to do, I didn't do this for this one, but let's calculate the characteristic impedance. So the characteristic impedance for that would be the square root. We know it's at a 45-degree angle, but it's omega, which is 2 pi times 10 to the 8th times mu, which is really going to be 4 pi times 10 to the minus 7th, right? Over sigma, and that's 5.8 times 10 to the 7th. What do you get for this intrinsic impedance? We know it's at an angle of, I'll just put the magnitude, it's an angle of 45 degrees. What do you get? You know, you can do these calculations right on OneNote. Did you know? Are you doing a calculation or not?
No.
You can actually do them, which is very nice. Because I do.
Is this the intrinsic or characteristic impedance?
This, well, it's the intrinsic impedance of this media, not free space. So when you do it, what do you get for this?
So 3.6 milliohms?
Yep. 6 milliohms at an angle of 45 degrees, right? What is it for free space? You just thought. What's the characteristic impedance or intrinsic impedance of free space?
0.
120 pi, right? About 377 ohms, right? What's the ratio of this? Now take a look at this. 3.6 times 10 to the minus third over what? 377. What is that? Want to guess? About 10 to the minus 5. About the same. Each one is knocked down by that much. Anybody want to tell me what that is? Just take 3.6 times 10 to the minus 3, that's milliohms, divided by 377.
9.8 times 10 to the minus 6.
About 10 to the minus 5th. It's of the order of 10 to the minus 5th, and it's the same level of decrease that the velocity was. That's important to take note of. The impedance drops proportional to the velocity. It's important. Okay. Now, one other thing. We did velocity. We did that. What is the fundamental definition for wavelength? Do you remember? Remember how we got wavelength? We always took the argument of what? Omega t minus beta z, and we saw if we froze time and just had beta z, so make t go to 0. We know cosine of minus beta z is the same thing with cosine of beta z, right? Because it's an even function. And when z is 0, would be the start of the wave phenomena. And when beta z was 2 pi, it would be one wavelength down, wouldn't it? So we had beta times the wavelength equal to 2 pi. Remember this. This will help you. So that means the phase velocity, the wavelength would be equal to what? 2 pi over beta. And what is that going to be for R's? I forgot what beta. Did we even calculate beta? We didn't calculate propagation constant, did we? Well, we can, since it's right there, we can calculate. But for R's, it's going to be 2 pi, right? Over beta, which is square root of pi f, which is going to be 10 to the 8th, mu, which is 4 pi times 10 to the minus 7. And then it's going to be sigma, which is times 5.8 times 10 to the 7. So what do you get for that? I left it in that form. I'll give you a hint. Whatever the free space wavelength is, it's going to shrink by about 10 to the minus 5. I mean, it's going to be 10 to the 5th less, just like the other stuff. It's 5 orders of magnitude down.
About 4 times 10 minus 5.
It's about right. 4 times 10 to the minus meters. Small. Everything's, conductivity goes down, velocity goes down, wavelength gets shrunk, and that's important to see. So now, after that, there was a professor named Dr. Thomas Shumpert here years ago, and he used to, at this point in the course, he'd say, I can run faster. How many think I can run faster than electromagnetic energy propagates in metal or in a good conductor? He made it dramatic, and like, he's trying to say, oh, like, that can't be, get people to say, but the minute he says that, everybody knows it has to be, he wouldn't say it. All right. Now we're going to talk about currents in metals and something called skin depth effect. Has anybody heard of skin depth in here? No? All right. Well, here's what happens really with electromagnetic wave. You know the general formula for an electromagnetic field, if it's propagating in the z direction, but it's oriented in the x, and this is just a positive traveling wave, it would be some E0, e to the minus alpha z times e to the minus j beta z, right? And it's in the x direction. Now, try to appreciate what I'm doing. I'm going to say I have something, and this is going to be a very good conductor. Which means alpha equals beta. And if I look at this, that's the E field, and that means that J would be sigma E field, and it's just sigma multiplying this. So if I looked at this, and I looked at J here, the value here would be sigma times E0, and it would exponentially decay. It would be decaying at the rate e to the minus alpha z, if we looked at the magnitude of J. Does that make sense to everybody what I'm showing you? I'm going into the metal. Z is in the direction of the metal. Follow me? Now if you look at that, this is the current. I'll try to give you a picture of what I'm trying to show you. Suppose we have a block like so. I wish I was a better artist, but I'll do my best. We have a block, right? And I'm going to say on this surface, there's going to be an electromagnetic field which gives rise to a current. And let's just say that this value right here, sigma E naught, we'll call J naught. So right here on this surface, this is J naught magnitude. Are you with me? And it's propagating in this direction. We'll call this the Z direction. Call this the X direction. And what's going to happen is these things are going to attenuate exponentially, each one of these. They're basically going to attenuate this way into the metal. Can you all see this, or into that block? Now try to appreciate this. If we give this a width, W, I've got with W, I've got this current flowing in it. And if I wanted to find the total amount of current that was flowing through this upper surface right here, you know, the current, the thing's decaying down there, but it's uniformly decaying. It's not a function of the vertical position. Follow me on this? And it's not a function of the horizontal as far as the value. It's only a function of the depth into the material, Z, as far as the value of J. So if we wanted to take a look at the total current penetrating that surface, I, the thing we could do is say we would take the current here that's penetrating the surface there, and we integrate that current over the entire length So I could say I would be equal to the integral, be a double integral, because I've got to go this way as far as this way. We go from 0 to W, and from 0 to, I'll call this point L on a Z direction, of the current density, which would be J naught, which is sigma E naught, times E, and I don't want just magnitude of I, so I don't need a phase, E to the minus alpha Z dZ, and it would also be dy. Remember, that's X, that's Y, that's Z. Follow me in this class? I'm trying to make this easy. Sometimes it's not easy, but so that's the Y direction, this is the Z direction. You all agree that that would be the total current penetrating that upper plate right there, right? We're going to do something. We're going to let this thing L, the length of this thing, go to infinity. So we're basically saying it's just going to be as long as it can be. All right? Now, how much current is that going to be? Well, that current would be sigma times E naught. Then when I integrate dy from 0 to W, it just brings out the width, W. And then I integrate e to the minus alpha z, becomes minus the quantity minus 1 over alpha, then it's e to the minus alpha z evaluated from 0 to infinity. Now the only thing I've done there is the dz integration. When I integrate minus alpha z dz, I get 1 over minus alpha times e to the minus alpha z, and I have to evaluate it between 0 and infinity. Do you all see that, class? Now this is a trick I use all the time. You see that's minus sign right here? If you got a minus sign, what you can do is just invert the limits and get rid of it. So now, instead of going from 0 to infinity, it goes from infinity to 0, only it's positive. And now when you look at this, this is really going to be sigma times E naught times W over, or times 1 over alpha. I'm going to leave that alone. And then it's going to be, well, E to the 0 is 1. It's 1, and then e to the minus infinity is 0, so it's just this. And that is the total current I. Do you follow me on this? Now, listen to me carefully, this is important. What we'd like to do is say that what this really is the current density J at the surface, J naught, or I like to say it. And that's J naught's the current right here, right? We're going to multiply that times the width. So that would be multiplying the current density times width, but current density is really amps per meter squared, so we need a depth. You follow me? And here we use the term skin depth. And this is the skin depth. And the skin depth is given the symbol delta, and it's equal to 1 over alpha, and that's equal to 1 over the square root of pi f mu sigma. Now this is important. This is skin depth right here. And the why that is so important is instead of doing this crazy integration all the time, since I know I have this behavior, I can say if I want the total current flowing in a piece of metal, and I'll give you a couple examples in a second. What I can do is simply say I have the surface current. I simply multiply by the width that way and 1 skin depth into the thing. Now, 1 skin depth down is effectively the distance you have to go so you take care of the entire amount of current that's flowing in there. And really, what I'm going to say is this. When I'm 1 skin depth down, and you can show this, the value here is going to be 33% less than that. So this value is going to be 37% of maximum. And that maximum would be here. Y'all see what's going on here? Keep that in mind. Now, here's where skin depth is really applicable. It's the problems where you talk about resistance of certain things, like wires. Have you realized that a lot of times when you're at high frequencies, they don't use solid pieces of metal. They have hollow pieces of metal. Does anybody know this? Well, the reason is because all the current's on the surface. None can penetrate down to the core because of the skin depth effect. So they developed something called the high frequency resistance of wires rather than just low frequency. So let me go through an example. This is skin depth, and it's an example. All right, now suppose I have copper, which has sigma equal to 5.8, pardon me, times 10 to the 7th, and 1 over ohms meters. And I'm at a frequency of 10 megahertz, right? And now I have some wire, and let's say the wire has a radius of 1 millimeter, and the wire has a length of 10 meters, and I want to know the NTN resistance of that, but I want to know it for DC. DC means for DC current, nothing time varying. So I've got 1 millimeter as the radius, that's equal to R. The length is 10 meters, and I want the DC resistance, and I gave you the conductivity. DC means it's not a function of frequency. So what's the equation for resistance for something with a constant cross section? You remember this from me, Megan? Anyone? You guys aren't talkers, are you? You need to get on a radio talk show for a while. Called Feinbaum. Have some fun. All right. You know who Feinbaum is?
Yes, sir.
How many do? At least I can see you're alive. Yes, good. They're all. Yes, I've never called, but I've always wanted to call. Call myself like Bubba Thompson. I'm a big fan of Miami and Auburn, Tennessee. That's God comedy. I want to ask you why you're a communist. Something like that. It really just, he doesn't know where to go with it. What he's saying. Talk show hosts get punked all the time, by the way. Do you know who 4chan is, anybody? Oh boy, have they done some doozies. I've listened to these guys. Every time somebody calls me on the phone, it sounds weird, I'm always thinking somebody's having fun. All right, the DC resistance is a long bar. Anybody remember it? Let me ask you this. You think it's proportional to length or inversely proportional? The longer something is, the more resistance, right, between the ends? Isn't that just proportional to L? Yeah, it's proportional to length. What about cross-sectional area? As area gets bigger that the current's flowing to, does resistance go up or down? Down, right? Think about putting things in parallel. Parallel resistors, so it's inversely proportional to area. You guys are on top of it now. And is it proportional, inversely proportional to conductivity? Just think about it. Inverse, right? And that's the general formula for resistance for anything with constant cross-section between the ends. Now let's DC. In our case, area is what? Area is a circle. It's really a circle, or it's simply what? A plate, a circular plate, right? That's where all the current's flowing in. We're assuming the current flows in this way, comes out this way, creates a voltage, and the voltage divided by the current would be the resistance, right? All right, now the length I gave is 10. The sigma is 5.7 times 10 to the, or 5.8 times 10 to the 7th. And what's the area for 1 millimeter, something with a radius of 1 millimeter? What is the formula? It's pi times what? Times a squared, right? So it's 10 to the minus third squared. And you can give me a value for that. That's RDC. When you get it, just let me know. So we're going to calculate the skin depth, which is 1 over the square root of pi f mu sigma. And somebody's going to have to do this for me, but it's pi f, and f is 10 megahertz, or 10 to the 7th, 10 to the 7th, times mu, 4 pi times 10 to the 7th, times sigma, and sigma for copper, I'll put it right here. Yeah, I did it right here. Is 5.8 times 10 to the 7th. Give me the skin depth. do this calculation. Anyone? Help me, my friends.
See, I got RDC.
Oh, good, what did you get?
I got 55 million.
Great, 55 million. 55 millions, not millions. What about the skin depth? You're gonna see how these millions go way, way, way out at this frequency. I think.
6.6, is it in meters?
Microns, right?
Micrometers?
It's 10 to the minus 6, isn't it?
Yeah.
6.6 times 10 to the minus 6. Now, do we all agree that the radius A is much, much greater than the skin depth? You all agree with that?
Yeah.
And if this is the case, then you can do this. Now listen, you can go ahead and look at that wire's cross section. We know the wire is radius A, right? But now the signal is only penetrating, and it penetrates from the outside of the wire in, is only penetrating one skin depth. So that means it's only coming in one skin depth. And if I draw around here, I can say if I go one skin depth in there, that's now the cross-sectional area. You follow me on this, class? There's two ways of doing it. The easiest way is just assuming that you take the length of the perimeter and multiply it by the skin depth. Cut this thing in half and then lay it out flat. So it'd be a skin depth thick and 2 pi times the radius in length. Do you follow me? Everybody, give me a show of hands here. Sure. I mean, the outer perimeter is 2 pi a, right? It's one skin depth thick, cut it in half and just lay it flat. Or the other way is take the outer area, pi a squared, and subtract out the inner area, which is pi times a minus the skin depth squared, right?
Yeah.
That would do it too. In any case, the actual area associated with this is approximately, to a high degree of accuracy, 2 pi times the radius a times the skin depth. In our case, it's 2 pi. The radius is what? 10 to the minus third, right? And the skin depth is 6.6 times 10 to the minus 6. So that's the area. And now look at the resistance, RDC. I mean RAC. This is actually call it RHF, high frequency. Now it's still a length of 10, right? And it's over sigma 5.8 times 10 to the 7th, but now the area is down to whatever that is. And you guys, that's 10 to the minus 9, so it's whatever this area is, call it area high frequency. Can you give me this? What? 4 ohms. We went from 55 milliohms to 4 ohms. Now my point is this. This wire I'm showing you here, I don't know what American wire gauge it is. I think it's 26 gauge wire, but I'm not absolutely sure, so I don't want to say that for a fact. But this is a representative piece of wire. At very low frequency, at DC, it had about 55 milliohms, which is trivial. So if you're connecting that to an 8 to 10 ohm, something with equivalent to 8 to 10 ohms of input impedance, there's no big drop across that wire. Do you follow me? Even 2 pieces. But when you get up to 10 megahertz, now you have 4 ohms in each wire. It's going to be a differential circuit, right? The current's going to flow down one, come back the other. That's 8 ohms total. If your load is of the order of 8 to 10 ohms, you're losing half of your voltage in the wire. Are you with me on this? And the way to beat that, and that's the way they always do, there's 2 ways. Have you ever noticed, you know what twisted pair cable is? Well, you can find cabling that just is individual strands, very thin strands of copper, wrapped with an insulator that are woven, and they're like bundles, there are hundreds of them. That will get rid of the skin depth phenomenon. Another way is to just have a big wide piece of pipe and have just a very thin piece of it. In other words, all it is a shell, and it's hollow on the inside, because all that current's flowing on the outside anyway. Usually what they choose to do is use a whole lot of thin fibers of wire coated with plastic or an insulator and bundle them. And that's twisted pair bundling. It's so they can get more of the signal down line without the attenuation, just the actual ohmic attenuation. Y'all appreciate that? Now, I know I showed up 2 or 3 minutes late, the class is about over, but let me just mention one last topic, all right? This is kind of important. By the way, what's the weather today supposed to be? Anybody know?
I think rain in some parts of the state, but I ain't sure about here. I don't know.
I'm kind of curious. In Alabama, you can never be sure. I've gone out jogging where there's like a 20% chance of rain. Came back about 30 minutes later, it's pouring down, soaked. It's really hard to tell sometimes. All right, now we're going to be talking about power flow. I want to just get this out here so I can get this topic to you. Now, power is something you're very familiar with from both, how many had gross or your power course, right? And it was always in voltage times, or really voltage multiplied by current conjugate, right? Times the real part of that times 1/2. Well, when you talk about average power flow, please just write this down, average power flow. The symbol is actually SAV. He doesn't use it in his book, and this is called a pointing vector. And that's 1/2, this is the definition, the real part of E cross H conjugated. It's just like E is like voltage, H is like current. E has the units of volts per meter, H has the units of amps per meter. It's very similar. This is for, by the way, for really for steady state operation. Think in the omega domain. It's not instantaneous. This is only for steady state, but that's the most common way it's done with. Instantaneous power flow, P of T, and this is in watts per meter squared, by the way. Instantaneous, SAV of T, is simply E of T, vector crossed into H of T, vector. There's no conjugation. That's instantaneous, but almost always use steady state power, or average power. So, now I am going over a little bit. I'm going to pick it up there next time, and I'm going to go ahead and show you power flow in lossy materials and in low loss materials. And then we'll get into the reflection of waves. Are you with me? Now please do your homework. I'm going to put up there. Everybody's got a book, right? See you on the